Okay, thank you for the introduction, Mr. Chair. Good afternoon, everyone. I hope you had a nice lunch, and hopefully you will not be able to sleep during my presentation. Okay, so my name is Rico Maestro, and this is my PhD work in Leuven in collaboration with the company Xenics. So basically, what's the motivation of this work? So we see two trends in the field. In the image sensors, we have that trend. Basically, we see that the pixel pitch keep on decreasing, right? At the same time, we have another trend in the intelligence or machine learning AI field where we're pushing the intelligence from the sensors, from the servers down to the sensors themselves. And for these two trends to combine properly, we think that the best or the most efficient way is to have the digital data inside the pixel themselves, which means that you will need to have conversion inside the pixel in a parallel fashion. Okay? And for that case, we use a pulse frequency modulation-based ADC, as shown in this block diagram and timing diagram. So what happens here is basically during the integration time, we are counting the number of charge packets Cint times the delta of that node Vint, which is, yeah, as I mentioned earlier, during the whole integration time, right? So, sorry. So what happens is that that node V clock counts or is used as a counter or as a clock of the counter there, which is basically with linear relationship with the photocurrent. Okay. Now, during this design, these are the requirements that we have. So we want to have a maximum pixel pitch of 10 micrometer. We want to have a low power consumption that's less than 1 microwatt per pixel. And we also want to have high dynamic range and low read noise during high gain settings. So that's around 60 dB dynamic range for a full well capacity of around 15 kilo electrons, right? And we also want to have very good SNR throughout the whole input range. So, and speaking of SNR, we think that, okay, since we have conversion happening inside the pixel, an additional factor in the read noise there is also the quantization noise. And as I mentioned earlier, what happens is we're counting the charge packets. So basically, that output T out that we have, the LS bit there is just that Cint delta Vint, which we need to reduce, right? Which is quite difficult because for our case, that Cint is not an actual capacitor, but just the parasitics of that node there. And the delta Vint, we really cannot go very low because of the possible mismatch that could happen or the offset in the comparator. So we need to have some margins there. So in a very optimistic fashion, say for example, if you have a capacitance of 1 femtofarad and a delta Vint of 15 millivolts, we will be having an LSB of 312.5 electrons. And that's quite too high for our applications. So what we decided is to have another step in the conversion process to further quantify that residue at the end of the integration time. Therefore, having a two-step conversion where the first step is again counting the charge packets, and the second step is basically measuring the time until we get, or until the charge packet, the last charge packet was finally completed by the photocurrent, right? So we have here now an external clock FRES that is used as a clock of this counter to measure that time value. And based on that mechanism, we have these equations as shown here. You can see now that the number of integrated electrons is not that as straightforward compared to as before. You have more complex equation now here. And from there, we can see that the LSB also is not uniform throughout the whole range. It is non-uniform, as we can see both the outputs D course and D residue in that equation. And also in the LSB, we see a new variable coming in, the FRES. So the question is, how are we going to set the value of that FRES, right? So a first case, for example, if you put that FRES in a low value, say around 4.2 kilohertz, and let's assume that we have a sample system with those specifications on the corner, and we can compute basically the LSB and the integrated number of electrons based on the previous equation, we'll be having something like this on the graph. What's good is that, okay, we have very small LSB, meaning we will be having a good dynamic range, but the problem is that at the middle and high input values, we have an NLSB that is almost equal to our charge packet. it's assumed that we're not using the residue conversion anymore, right? So what if now we set the FRES to a very high value, say 800 kilohertz or around that value? We will have a very good quantization throughout the whole input range. That's 20 electrons throughout the input range. But the problem now is instead of having 6 bits of residue counter, we will be needing at the maximum more than 10 bits of residue counter to satisfy and to sense all the input range that we have from a minimum photocurrent of 10 femtoamperes. And having more than 10 bits of counter inside a 10 micrometer pitch is just quite difficult to do. So we think, okay, we are seeing with a low frequency, we see benefits in one edge, or sorry, one side of the system, bad on the other side. For the high value, we have problems on one edge, and good values or good performance on the other. So why are we restricting ourselves with just one residue counter value? So we implemented something with multiple FRES value. So just for an example, an exaggerated scenario where basically we have 16 clocks. Again, this is not what we did. This is just an exaggeration. We have 16 clocks, right? We can see here that you have good quantization throughout the whole range. Instead of having 12 D-course value with residue, now we only have 3. But the problem is we have a lot of clocks, meaning increased power consumption because you need to generate all of this, increased routing complexity because you need to deliver all of this clock to the whole pixel array, and of course increased area and logic for the logic inside the pixel, right? So upon seeing this, we reminded ourselves when we were in the thinking process, right? We reminded ourselves, okay, we are designing an image sensor, a conversion for an image sensor, meaning eventually our SNR will be dominated not by the read noise anymore, but in high input, we will be dominated by the shot noise, right? There's always shot noise in our SNR there. So having, for example, if you have a shot noise of, say, 100 or maybe 200, depending on your input electrons, having an LSP of 20 electrons or less might be just an over-design to our system. So we try to relax these limitations that we have, this specification, such that the LSP will be less than or equal to that shot noise, right? So that gave us this system here, where basically we have only 3 clocks, right? We didn't use the very exaggerated part where we have 16, but now we only have 3 clocks, and we are together. We are in the same, or at least they are continuously in terms of D-core. So it's easy to make the logic in choosing which FRES value to choose, right? The only problem with this is that instead of measuring 10 femtoamperes minimum input current, we only can measure down, up to 51.9, starting at 51.9 femtoampere. But just remember that that is for integration time of 1 millisecond. We can further decrease this by increasing that integration time. Okay, so is it good to go? Okay, right? So we made an initial design, initial iteration, and we see that 80% of the area of the pixel is occupied by digital circuits, right? Meaning the remaining 20% will be occupied by the analog functionality that we need still in the pixel. Even though it's called digital pixel, we still need analog functionality inside that pixel. And implementing this with a small area, we will be needing to have simple circuits, small transistor sizes, which actually limits our performance in terms of linearity, reliability, and noise, right? So we still thought, or we still think, maybe we can still further decrease the digital parts of the pixel so that we have more area for the analog functionality. So what we did is we analyzed again the system, as you can see here, and we see, okay, this V clock here, it looks like they are events, right? So why not we change the system architecture such that we have a frame-based output as for the images, but we use like an event-based mechanism to be able to count these events here, right? So from this kind of system architecture, which you have a 20% analog, 80% digital, and all of your counters and logic are inside the pixel, we change that such that all the logic and the counters are in the periphery of the pixel array. yes, they are not physically inside the pixel, but virtually they are still inside the pixel, right? But now you were able to save area for your analog. So instead of having 20% of the area for the analog, you now have 80% of the area, which allows you to make better circuits for that. And as I mentioned earlier, the pixel pitch is still the same. It's still 10 micrometer for your photodiodes, but you have more area for your ROIC, basically. And as I mentioned, because of the freed area from the digital circuits, you were able to implement analog circuits, better analog circuits. Even in the layout, you were able to put guard rings to shield or at least isolate somehow the analog sensitive parts from the remaining digital parts inside the pixel. So we made the proof of concept chip where basically we have this in TSM 65 nanometer with the said area 1.3 millimeter by 1.3 millimeter. So note that this is just a proof of concept. So this is not intended to have hybridization of the INGaAs pixels yet. So which means we have only a small number of active pixels there. You can see 16 by 20. And as I mentioned earlier, we're targeting 10 micrometer pixel pitch, but for this proof of concept chip, we have additional 2.5 in the width to add 4 test current injectors. But eventually, when we're going to hybridize an actual INGaAs sensor in here, we're just going to remove that 2.5 micrometers there to have a pixel pitch of 10 micrometers. Aside from that, the counter arrays, earlier in the sample system, I have 4 bits for the cores and 6 bits for the residue. We added additional one because now we have sort of freedom in terms of the area of the digital. So we added more, 1 bit for each to account or as margin for the local variations. So some measurement results. In average, for a given delta V int of 200 millivolts, we have an average charge packet of around 2,700. So that charge packet is also basically tied to the full well capacity of the whole system, right? It's basically the cores, the maximum cores value times the charge packet. We can change that depending on the value of the delta V int. So the pixel non-uniformity of the system is 13.45, and based on the EMVA 1288 standard, the nonlinearity is 0.21%. We also see that the measured SNR is as close as the shot noise limited SNR, and based on, in comparison with other state-of-the-art works, and we think that we are at par or even better in some of the aspects. We see that our power requirements were met. It's less than 0.188 microwatt per pixel. That includes the power of the digital, the power of the biases, the power of the clock generators. And we see that for a SWIR sensors, we have the smallest pixel pitch as of the writing of the paper, and we have high dynamic gain also for high gain in SWIR. So in conclusion, we were able to implement a PFM-based two-step ADC that allows per pixel conversion, and we see that we have a non-uniform quantization that allows for high gain, allows high dynamic range for high gain in 10 micrometer pixel pitch, and we used an event-based system to increase the allocation for the analog circuit to make our performance better. So just an acknowledgement, this work is funded by the VLAI Research Project, and thank you very much for listening to my presentation.